When Cerebras secured a massive capacity deal with OpenAI, headlines called it a chip victory lap. But for AI engineers watching from the trenches, this isn't about one winner. It signals that the decades-old strategy of simply buying more GPUs has hit a hard wall. The physics of scale are failing us right now. For 10 years, the engineering playbook was brutally simple. Buy more NVIDIA H100s and stitch them together into a massive cluster to solve scaling problems. If you needed faster training or bigger models, you added another rack, then another switch, and kept stacking until your power budget ran out. The recent Cerebras deal proves that this distributed model is no longer sustainable. It marks the moment we stop betting on more GPUs as a silver bullet and start facing the brutal reality of diminishing returns in infrastructure management. Engineers who continue to rely on scaling out by adding commodity hardware are building systems with escalating failure rates, crushing energy costs, and software overheads that can no longer be ignored. The industry is pivoting from distributed clusters toward monolithic ASIC architectures where memory bandwidth dictates success far more than raw compute speed ever did. This shift changes everything about how we design systems today. The first thing to understand is that the physics of scale have fundamentally broken under current conditions. We are hitting a ceiling not just on cost, but on energy and environmental impact. Current frontier model training consumes power comparable to hundreds of households per run. Research led by industry figures like Yann LeCun confirms that relying on scaling GPU clusters has hit diminishing returns due to these infrastructure constraints. The metric the world is now prioritizing is intelligence per joule rather than raw flops, a standard where distributed clusters struggle significantly compared to co-designed monolithic systems. We are looking at targets for efficiency improvements of 1,000 times by 2035 because the current trajectory is physically unsustainable without radical architectural changes. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. We see this failure mode clearly when we look at real-world deployment data from massive supercomputing efforts like Sakura-Oni, which ranks on global top performance lists with open Ethernet stacks scaling to around 800 GPUs. While these systems demonstrate that you can technically stitch together hundreds of nodes, the complexity of managing distributed failures and software overhead remains a critical bottleneck. As data generation from complex simulations hits 10 gigabytes per node daily in fields like biomolecular engineering, storage input-output and network latency become choke points that raw compute power simply cannot solve. The buy more strategy increases downtime significantly because every additional link in the chain is another point of failure requiring specialized infrastructure investment just to keep everything running. This reality forces a hard pivot toward monolithic architectures, where we stop trying to move data between thousands of separate nodes and instead process workloads within a single die or tightly integrated unit. The Cerebras deal validates this shift by demonstrating how wafer-scale engines eliminate the interconnect overhead that has plagued distributed clusters for years. Instead of wasting time moving tensors across network cables, these architectures keep memory local to the compute cores where it is needed most. This mirrors a broader roadmap emerging in developer communities to move from scaling out designs to designing up physical silicon constraints. We are seeing software and hardware co-designing for specific inference tasks rather than relying on generic training clusters that try to do everything but fail at optimization. However, there is also a psychological trap holding engineers back from making this necessary shift. A critical behavioral risk exists where professionals treat the promise of more compute as an infallible predictor of success. In studies involving over 1,300 participants regarding AI decision-making, researchers found that 40% or more treated artificial intelligence systems as authoritative predictors they could trust implicitly. This led subjects to forego guaranteed rewards and make suboptimal decisions based on belief rather than architectural reality. We see this same pattern in our industry, where engineers assume adding another GPU will solve a bottleneck without questioning whether the underlying architecture is even capable of handling the load efficiently. The data shows that over 40% of people treated an AI as an infallible authority, leading to financial losses ranging from 10.7% up to nearly 43% when they made decisions based on false confidence in predictive power compared to random framing conditions. This behavioral bias is dangerous for system architects who might skip necessary architectural reviews because they trust that more compute will fix the problem later. It creates a cycle where we keep buying hardware instead of fixing software and design flaws, leading to systems that are incredibly expensive but fundamentally inefficient at their core tasks. For you as an AI architect or engineer, your career is standing at this exact pivot point right now. If you continue to specialize solely in distributed cluster management tools like Kubernetes tuning or MPI optimization without understanding the shift toward monolithic silicon, your skill set faces rapid obsolescence. The projects are migrating away from generic cloud instances toward edge-optimized inference engines and specialized ASICs where memory bandwidth matters more than raw throughput. The practical path forward requires you to stop optimizing for scale-out strategies that no longer yield proportional returns. You need to focus on memory bandwidth, KV cache management, and single-die efficiency through kernels optimized for specific hardware architectures rather than generic clusters. The future belongs to engineers who understand how software stacks map onto physical silicon constraints instead of just provisioning cloud instances and hoping they work. Mastery of intelligence per joule and hardware-aware coding is becoming more valuable every day because the days of throwing money at GPU farms are ending. You must learn to design for efficiency, not just raw capacity, or you will find yourself managing a system that works but costs too much to run. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.